My name is Aniket Deshmukh, and thanks for listening to this talk on our work on performance characterization of .NET benchmarks. I'll start with what .NET is and why it is relevant to study applications built on top of this framework. I'll then go over the open source benchmarks that we used and the representative subset we generated from these initial workloads. Then I'll explain how we characterize the performance of these applications in hardware, which includes basic performance counter studies, top-down analysis, and runtime event correlation. Finally, I'll talk about a few interesting research opportunities enabled by our work. Managed languages are quite popular today. These languages have managed runtimes that perform tasks such as just-in-time compilation and garbage collection, which makes them very different from traditional workloads such as SPEC. .NET is an open source cross-platform software development managed language framework introduced by Microsoft, and is an important managed language framework that has not been well studied. Our work is the first to present a detailed hardware characterization of .NET applications. Other managed languages such as Java have been explored before, and there has been prior work on creating Java benchmarks and analyzing its impact on the microarchitecture. However, .NET and Java are substantially different. For instance, Java's JIT optimization techniques and heuristics for JIT compilation are different from .NET's. Threading, algorithms, and heuristics for garbage collection also differ between the two. Moreover, .NET is a popular development framework that is used both in the client and server space. Many Microsoft data center services are built on the .NET framework. Its popularity and intrinsic differences with Java make .NET an important target for architecture and microarchitecture studies. To ensure our work can be picked up by the community, we targeted open source .NET benchmarks. We found two major sets of applications. The first, .NET performance benchmarks, are used for testing the performance of a large swathe of .NET libraries. They contain a collection of system-level and application-level benchmarks. The system-level benchmarks test simple .NET libraries for file I/O, network transmission, and so on. The application-level benchmarks include real-world applications and algorithms which use complex data structures. The ASP.NET benchmarks are built on top of the ASP.NET framework, which is used for developing web applications. They essentially model client-server workloads, and in our analysis, we focus on the server-side performance. Since dealing with a large number of workloads is difficult, we recorded an initial set of metrics for all benchmarks in order to group the similar ones. For data collection, we used an Intel Core machine. Most of our experiments were done on this machine. The Intel Xeon machine was used to verify that the reduced subset of benchmarks we obtained was representative. We also collected data on an ARM server machine. We don't go over this in the presentation, but the results of our analysis are available in the paper. For obtaining representative benchmarks, we used a mix of intrinsic program characteristics, microarchitecture events, and managed runtime events for the .NET workloads to cover a spread of architectural and microarchitectural behavior. Since we had a large number of metrics to work with, we used principal component analysis to eliminate the redundancy among them and reduce it to a smaller set. The PC analysis generated 24 principal components, from which we picked the top 4. The details of this process are shown in the paper. With these principal components, we used hierarchical clustering, shown on the left for the .NET benchmarks, to cluster the workloads. We settled on 8 clusters for each suite and randomly picked one benchmark from each cluster to construct our representative subsets for .NET and ASP.NET. We also added the SPEC CPU17 benchmarks, which were clustered similarly to this list. We show the results for SPEC-17 along with our benchmarks for the rest of the analyses to provide a point of comparison. Since the principal components form orthogonal vectors, we can also use them for comparing the benchmarks. We used PCA on control flow and memory-related metrics separately to examine their behavior independently. Looking at the figure, benchmarks across all the suites exhibit different behavior since the data points corresponding to their performance characteristics don't coincide. However, ASP.NET and .NET benchmarks are similar in terms of their control flow behavior. This is attributed to the common runtime across the two, since it contributes a fair bit to the control flow complexity of these benchmarks. As part of our characterization, we also collected basic performance counter statistics. When we look at a few microarchitecture independent metrics for the three benchmark suites, we see that .NET and a few ASP.NET benchmarks execute a high percentage of kernel instructions. This is mainly due to the networking stack in ASP.NET and other managed runtime operations across both the suites. The user code in .NET and ASP.NET benchmarks is relatively simple. And again, this, along with the common runtime shared by the applications, works to reduce the variety in the instruction mix we observe. Moving on to a few microarchitectural metrics, we observe that the ITLB and iCache MPKIs are inordinately large for ASP.NET and some .NET benchmarks. This is attributed to the large code footprint of these applications. Frequent JIT events also contribute to this, and we'll discuss the effects of these runtime events in further detail over the next few slides. Branch MPKIs for the integer SPEC benchmarks is high since they perform complex control flow operations. Certain .NET and ASP.NET benchmarks are also prominent in terms of branch MPKI because of branch mispredictions in the managed runtime and cold starts associated with JIT events. As far as the CPI is concerned, the ASP.NET benchmarks are much slower compared to the rest, since they are primarily bottlenecked by memory. To understand these bottlenecks better, we use the top-down methodology, which tries to outline the bottlenecks in program execution by looking at how well the processor pipeline is being utilized. To do this, we calculated the number of pipeline slots in the core. Intel cores provide performance counters that allow us to measure pipeline slots that are empty and allocate a bottleneck to them, thus giving us a performance profile for each benchmark. Looking at the top-level breakdown, we see that the ASP.NET benchmarks are significantly back-end bound. Data center applications tend to be memory bound, and our analysis is in line with this observation. SPEC programs generally exhibit more complex control flow behavior and hence have a broader spread of misprediction-related stalls compared to the managed language benchmarks here. One thing to note is that the ASP.NET and .NET applications are not as front-end bound as the high iCache and ITLB MPKIs would suggest. To investigate these bottlenecks further, we zoomed into the front-end and back-end bound distributions. Front-end bottlenecks are broken down into bandwidth bound and latency bound metrics. Bandwidth bound represents instruction slots lost due to fetching instructions at less than peak bandwidth due to things like packet breaks and structural constraints of the decoder. Latency bound metrics cover slots lost due to stalls in the front end. We see that the three bottommost components, BTB misses, ITLB misses, and iCache misses, are fairly large for some ASP.NET and .NET benchmarks, particularly the BTB misses. However, it's worth noting that stalls in the front end can be hidden by backend stalls. For instance, iCache misses don't generally affect performance significantly if they hit in the higher levels of the cache hierarchy, because these can be hidden effectively by other long latency stalls. This is exactly what happens in ASP.NET, which is memory bound. The iCache latency doesn't bottleneck these applications as much, even though the MPKI numbers are very large. Looking at the distribution of bottlenecks in the backend, we see that the ASP.NET benchmarks are L3 bound. A large fraction of the empty pipeline slots in these benchmarks are thus due to LLC misses, since in the basic breakdown, ASP.NET benchmarks are primarily backend bound. However, the per-core LLC MPKI for ASP.NET is not larger compared to the rest. We also observed that the L3 bound component increases for these benchmarks as we scale the number of cores on which they are run. This indicates that the LLC access latency is the primary bottleneck here. This happens because of increased contention at the LLC slices and an increase in the network on chip traffic. This kind of behavior has been observed before in large multi-threaded applications. Most of the ASP.NET and .NET applications have working set sizes under 500 megabytes and are thus not DRAM bound. Finally, a significant percentage of empty slots are due to decache-related stalls in ASP.NET and select.NET benchmarks. This indicates that there are a large number of simultaneous requests to the decache that are hits, which saturates the decache bandwidth in these applications. Moving on from the top-down analysis, we note that the managed runtime is an important component in .NET benchmarks. To measure its effect on microarchitecture, we perform correlation studies for two major runtime events, JIT calls and GC invocations. And we do this by obtaining an overtime performance profile for the ASP.NET benchmarks. When we look at how the performance counters correlate with JIT events, we see a strong positive correlation with branch MPKI, LLC MPKI, and page faults. The increase in these metrics is between 5 to 20% over the running average. We also see a minor increase in the L1 high cache MPKI. These effects can primarily be attributed to cold starts. A code page is normally mapped to a new address after being JITted, and thus results in cache misses and page faults when they're next fetched. Structures in the microarchitecture that store metadata tagged with the PC, like branch predictors, are also similarly affected and incur cold starts. It is worth noting that while the managed runtime code corresponding to the JIT engine also contributes to these increases, the sample performance counters indicate that a large proportion of the increase was indeed due to the JITted code pages. We also see a slight negative correlation of JIT events with the number of useless prefetches. Once the initial misses have been satisfied, the prefetcher is able to cover some of the subsequent misses. However, the corresponding increase in LLC MPKI suggests that these prefetches aren't aggressive enough. Moving on to the correlation results for GC events, we surprisingly see a decrease in the LLC MPKI. This can be attributed to two effects: removal of dead data structures from the heap and rearrangement of data in memory, which the garbage collector does as part of heap compaction. This helps improve locality of long-lived data in the cache hierarchy and hence shows up prominently in the LLC MPKI. Note that the number of instructions on the core does increase on a GC event. This overhead of executing GC code on the core has already been well explored in prior work. However, in our benchmarks, the benefit of better locality in caches ends up outweighing the cost of GC invocation, which is reflected in the positive correlation of GC invocations with IPC. Our correlation studies reveal that there are many interesting opportunities for performance optimizations that either address or leverage the managed runtime. For instance, relaying metadata for JITted code pages to the hardware could help improve prefetching for those pages. The metadata can also be used to preserve or transform the microarchitectural state of the machine, such as branch predictor tables, to prevent cold starts. Hardware acceleration of GC can improve performance, not just because it reduces GC overheads, but mainly because it can improve cache performance. There has been prior work on garbage collection that tries to reduce the LLC MPKI purely through runtime optimizations, but this incurs the overhead of more frequent GC operations, which is really not an issue if you were to do GC in hardware. Going go even further, the hardware has detailed information about the cache hierarchy. Select memory management operations, when implemented in hardware, can improve cache performance through aggressive deadblock elimination and better mapping of data to cache blocks. While this is applicable to all kinds of programs, managed languages are unique in that the managed runtime can be leveraged here, since it has a large amount of metadata for live data structures already available, and it can share this easily with the hardware to enable such optimizations. As an example, the concept of GC generations, which classifies data as long-lived or short-lived, can be used to improve the replacement policy in the last level cache. To conclude, we created a set of representative benchmarks for .NET frameworks and analyzed their hardware bottlenecks, which presented some interesting opportunities for optimization. A lot of the hardware optimization opportunities required software support. Managed runtimes already provide a lot of metadata that can be leveraged to implement such solutions without needing to involve the programmer. Given the increasing popularity of cross-stack optimizations to push performance, especially in data centers, managed languages like .NET are poised to gain further importance in future architecture and microarchitecture research. We hope to see more work in full system analysis of these applications and microarchitecture optimizations for them. Thank you.